Hi class, today we are doing 4.7 on inverse trig functions. So some of the objectives is we're going to evaluate and graph the inverse of trig functions, and then we're going to evaluate compositions of trig functions in the second video. Okay, so for the graph of the inverse trig functions, I'm going to show you the graphs. We are not going to graph them. I'm going to show you the graphs because what's important from this section is the domain and the range of the inverse trig function. So we're going to graph just so we have a visual of what the domain and the range needs to be. So we're going to do the inverse trig function. So what I need you to remember is for the inverse of a function, you reflect your graph across the y equals x line, and that's how you get the inverse. So we take our graph, then we reflect it, and we have the inverse. And remember, for a function to have an inverse, it must pass the horizontal line test, the HLT. So if a graph passes the horizontal line test, then it has an inverse. Does the graph of this have an inverse? So what we're going to do is we are going to look at the graph, see if it passes the horizontal line test, so that we can draw in the inverse. Okay? So the first one we're going to look at is the sine function. So if we look at the sine function, and if we have just one function of sine, if we try seeing if it passed the horizontal line test, it doesn't, which is a problem when it comes to inverses, because to pass the horizontal line test, it can only touch it once for any horizontal line that you draw. So if I do what's called restrict the domain from here to here, and remember, if this value is minus pi, this is minus pi over 2 to pi over 2. So if I look at only this section of my sine, then just this section will pass the horizontal line test for all values, all horizontal lines that I draw through it. And so if I restrict my domain from here to here, then I can get an inverse. And remember, the way we get the inverse of a function is if we draw the y equals x line and we reflect across the y equals x line. So up here, this portion of sine would get reflected, and then over here, this portion would get reflected. So you can see the reflection here drawn in for the inverse trig function. So this is our inverse trig function. When you reflect across the y equals x line, and for inverses, the domain and the ranges swap. The x and the y swap. If you remember algebraically solving for an inverse, you would start with the function, swap the x's and the y's. So essentially, when we find the inverse, for the range was originally between minus 1 and 1 for this restricted amount. So its inverse, that would be the domain between 1 and minus 1. You see those values marked. And we restricted the domains so that the function, we're only looking at the part of sine between minus pi over 2 and pi over 2. So we see that becomes the range values from minus pi over 2 up to pi over 2. Here, 1/2 pi over 2. Okay, so the domain and the range values swapped. So the domain is between minus 1 and 1. Oops. Minus 1 is less than or equal to x, less than or equal to 1. And these are endpoints here. They're not arrows going on forever. The range is between minus pi over 2 and pi over 2. And on the unit circle, between minus pi over 2 and pi over 2, if you think of the unit circle here, down here is minus pi over 2, and up here is where pi over 2. So unit circle wise, because we are going to come back to the unit circle and we're going to find angles, the angle has to be a positive angle in quadrant 1 or the negative, I'm stressing negative, coterminal angle in quadrant 4. That's how it's between minus pi over 2 and pi over 2. So the negative angle in quadrant 4 or the positive angle in quadrant 1. Okay. So let's move on to arc cosine. So again, cosine, you can see, does not pass the horizontal line test, but we can restrict the domain so that it will pass the horizontal line test if we only look at that section. If we reflect this, we end up with this function here for arc cosine. Remember, we're not going to graph these, we're not going to shift them around, we're just looking at this as a visual to help us remember the domain and range, which is very important. So the range for cosine was minus 1 to 1, so that becomes the domain goes between minus 1 and 1. Here's my x-axis and here's my y-axis. I restricted it between 0 and pi. So this one is between 0 and pi. So my y values, right, so this was originally my x values, my domain, so that becomes my range is between 0 and pi. Okay, so now my domain is between -1 and 1. My range is between between 0 and pi. Okay, and on the unit circle, it's an angle between 0 and pi up here, quadrant 1 and quadrant 2. Okay, so anywhere up here in this section would be a valid angle. Okay, and it has to be between 0 and pi. For tangent, so we have the graph of tangent, and it had asymptotes at -pi/2 and pi/2. If we do the same sort of thing where we reflect it across the y = x line, these vertical asymptotes at pi/2 and -pi/2 become horizontal asymptotes at pi/2 and -pi/2. And the range was originally from -infinity to infinity for tangent, which becomes the domain. And these do have arrows going on forever and ever. So the domain is all real numbers. And then the range was between -pi/2 and pi/2, not including -pi/2 because it's an asymptote, and not including pi/2. So we'd say -pi/2 less than y less than positive pi/2. Now here I'm using the two different notations, and I am going to be using both of them. So I do want you to be comfortable using both notations. In this would be inequality notation. In the set or interval notation, you could of course write this as -pi/2 comma pi/2 with the round brackets because it doesn't include it. Okay, so the range on the unit circle, it's between -pi/2 and positive pi/2, so it's going to be the negative angle in quadrant 4 or the positive angle in quadrant 1. So remember, if it is a quadrant 4 angle, then you need to make sure it's the negative coterminal angle. Okay, so in example number 1, we're going to evaluate arcsine of √2/2. So this is going to equal some angle, okay, an angle. √2/2 is a number on the unit circle. √2/2 is one of the side lanes of the 45, 45, 90 triangle. Okay, so when we see an arcsine, we need to remember we're trying to find the angle. So we're going to rewrite this arcsine as a trig function instead of an inverse trig function with the arc. So sine of what angle theta equals √2/2. This is how we kind of rewrite it. Okay, so we cross it off over here. √2/2 equals sine of what angle. Okay, and we want to find what is that angle. So on the unit circle, we're going to figure out what that angle is. So the sine of what angle is √2/2? Sine is the y-coordinate. It's positive, so it's upwards in quadrant 1 and 2. And it's √2/2 at the, pi/4 and 3 pi/4. So there's two answers that make this statement true. The sine of theta is √2/2. However, we're going to look at the range of the inverse trig functions to pick the only correct answer. So remember, for arcsine, the range of arcsine from the previous couple slides was that it was between -pi/2 and positive pi/2. Right, so that was the range of arcsine. Had it be a negative angle in quadrant 4, the positive angle in quadrant 1. So the only correct answer for this is a positive pi/4. So to answer the question, we would say that arcsine of √2/2 is the angle pi/4. And there's only one correct answer, pi/4, because there's only one angle that fits the criteria, the positive angle in quadrant 1 or the negative angle in quadrant 4. And it has to be pi/4, not a coterminal angle like 9 pi/4, because that number is not between -pi/2 and pi/2. Okay, so here we're going to evaluate arc cosine of -1/2. So we're going to figure out what's the angle. Okay, so we're going to rewrite it as a trig function. So cosine of what angle is -1/2. Now remember, on the unit circle, cosine is the x-coordinate. 1/2 is a unit circle number, so that's how I know to use the unit circle. So if cosine is -1/2, cosine is negative. You remember, all students take calculus all of them in cosine are positive over here, so that means cosine is negative over here. So if cosine is negative in those quadrants, I want to know what are the angles. So for it to be negative 1/2, if I were to draw this a little more to scale, I would go over a little bit and up a lot. So it was actually the pi over 3 angle, so 2 pi over 3. And then the other one would be 5 pi over 3. Okay. No, that would be 4 pi over 3. Okay, so we found the two choices, 2 pi over 3 and 4 pi over 3 make cosine negative, but we're going to look at the range for the inverse trig functions. Remember, for arc cosine, the range was that y was bigger than or equal to 0 or less than or equal to pi. Unit circle-wise, it was between 0 and pi up there, which means we need to choose the 2 pi over 3 answer. So the answer is 2 pi over 3. Okay? Okay, so for example number 3, we're going to write theta as a function of x. So to write theta as a function of x, that means we're going to have something with a theta in it equals something with an x in it. Okay, so often in algebra class we'd write y as a function of x. We'd write y equals 2x plus 1, or something like that. We would have y equals. So here it's theta as, so something with the theta is as a function of x. Okay, so we're going to write x as your variable. So eventually what I'm going to do is I'm going to use an inverse trig function. So then I'm going to get it to be theta equals something with an x in it, because I want to use an inverse trig function. So I need to figure out which inverse trig function am I going to use. Okay, so I'm going to have theta on one side and x on the other. Okay, and then we're going to use an inverse trig function. So if this is my angle theta, this is the opposite, and this is the adjacent. So already for this unknown angle, I have information about the opposite and the adjacent. Using SOHCAHTOA, T-O-A, since I have a triangle, and it is a right triangle, I'm going to use SOHCAHTOA. Since it's a triangle, you can always use SOHCAHTOA, and tangent is opposite over adjacent. So I know that tangent of theta is the opposite over adjacent, and if I plug in things that I know, tangent of my angle theta is 3x over 2, because that's my opposite over adjacent. And this is writing theta as a function of x, but with a trig function, and I want to write it with an inverse trig function. So I'm going to write theta equals, so I'm going to bring tan to the other side by using inverse trig functions, tan inverse of 3x over 2. So now I've written theta as a function of x. So theta is some stuff with the x in it, and this is using an inverse trig function. If I had the opposite and the hypotenuse, for example, if my 2 was up here instead of down here, then I would have used sine of theta, and then I would have said theta is arc sine or sine inverse of that. So you just bring it to the other side. So finally what we're going to do is we're going to use a calculator to approximate the value of arc tangent of 0.75. So here's where I say, okay, I don't have a triangle, so I know I don't use SOHCAHTOA. This number is not on the unit circle, so I don't use the unit circle, which means I need to use the calculator. Okay, so the calculator is our last result. If we don't have a triangle, we can draw with it, and if it's not a unit circle thing. So I'm going to want my mode to be in degree mode, so we're going to have to change it to degrees, and we're just going to type this in directly. Remember, arc tangent is also written as tan minus 1 of 0.75. So I'm going to show you on the calculator how to type this in, but you do have this tan inverse button on your calculator, so we are going to press tan inverse once you're in degree mode, and then we're going to press 0.75 and then enter, and we should be good to go, getting an answer that your angle in degrees is 37 degrees. So I'll go ahead and pull up my calculator, and you should do the same. Okay, so here I am with my calculator. I need to make sure for my mode that I am in degree mode. So once you quit out of there, tan inverse is on the actual calculator, so you press second tan, and then 0.75, so that's tan inverse of 0.75. Press enter, and I'm going to round it to the nearest degree because that's what the directions said, and I get 37 degrees. Okay, so